Welcome to example number 9. In this question, we have a stone that is being thrown from the top of a building. So I'm going to just draw a little stick man here, and he's throwing a ball upwards, goes up like this, eventually reaches the top of its path, and then it comes straight back down, misses the building, and then eventually hits the ground around here. So we're told that the speed of the ball, we'll just write down the given down here. The speed of the ball initially at time 0 is 20 meters per second upwards. So this is the speed right here. I guess I'll just label that as a v sub 0 here. We're also told that the building is 50 meters high. Now we should decide on an appropriate coordinate system. Where would you like to put your origin, and what direction would you like y to be positive? Naturally, we normally make y positive upwards, and for an origin, you have two possible choices. You could either choose the ground, or you could choose the initial spot where the ball is being thrown. It's really up to you. I'm just going to choose for you, I guess, or you could do your own way. It doesn't matter, and just check your answers afterwards. I'm going to choose the ground. So y is positive upwards, and my origin is down at the ground level. Now, since I know that the building is 50 meters high, then I know that the ball is starting on my y-axis at an initial position of 50 meters. We're going to neglect the height of the person who's throwing the ball. So we'll assume that the ball is being, or the stone is being thrown at exactly 50 meters from the ground level. Okay, we know the acceleration, right? This is in free fall all the way through here while it's in the air, and that is negative 9.8 or negative g. You could replace g with 9.8 meters per second squared. Okay, and there's some other given information that we'll figure out on the way here as we proceed through the problem. Let's go ahead and start solving. In part A, we're looking for the time to reach the maximum height. So maybe we should label that position. That would be right here. We're going to label that as position 1. Is there any other given information that we know at the top of the path? Hopefully you got it. The velocity at 1 is what? It's 0. So that's going to help you solve for the time to reach the top of the path. We know the starting speed. We know the acceleration. We also know the final speed at the top, which is 0. So hopefully you're thinking of v equals v0 plus at. Let's modify that for the vertical direction. So v equals v0 minus gt, replacing the a with negative g. You don't have to. You could just replace a with negative 9.8. It doesn't matter. Final speed at 1, right? We're going from 0 to 1. So we have 0 as our final speed. Our initial speed is 20 meters per second minus 9.8 meters per second squared times t. We'll call it t1, by the way. And that will give you a time of, to 3 sig figs, about 2.04 seconds. Okay, that's part A. Let's go on to part B. Part B, we're looking for the height right here on the y-axis for that position. You could either report it from the top of the building or from the ground level. So I'm going to use my position function. Y final, y1 is equal to y initial plus the initial velocity times t1. I just figured that out, by the way, minus our plus 1/2 at squared. But you could replace the a with negative g, and you get this. And then we can substitute in. We have initial position of 50 meters. We have the initial speed is 20 meters per second. Time we just figured out is 2.04 seconds minus 1/2 times 9.8 meters per second squared times that 2.04 seconds again squared. And this gives you an answer of 70.4 meters. And we should be clear about what that is measured with respect to. And this is above ground. Not above the top of the building, but above ground, because that's where our origin is. If you had put your origin over here, then you would get an answer of 20.4, because it would be, you would be including the 50 meters in here. Okay, part C is asking for the time needed for the stone to return back to the level. So that's right back to where he threw it. We'll label that as 2. This is where he started at 0. And there's a lot of ways you can solve this. The fastest way is just to realize that the time up equals the time down. And so therefore you've already found the time up. It's 2.04 seconds. So the time 2, which is from 0 to 2, would be just really 2 times t1. 2 times 2.04 seconds. So t2 is just really 4.08 seconds. Now, there are other ways of solving it. I'll just show you that. You could, for example, I'll just put this as an or and then I'll erase it in a minute. You could just say, well, y2 equals y initial plus initial speed t minus 1 half gt squared. And this would be time 2 and time 2. And you know that the y2 position and the y0 position, they would both cancel out because they would be both 50 meters. They would be both coming to the same position. And so you would have 0 equals 20t minus 4.9 t squared. That's half of 9.8. And then when you solve this out, you'll get two answers. 2 equals 0 or t equals 4.08 seconds. And there you go. There's the answer. That's solving it mathematically. But you don't have to. If you can use some logic like this is totally acceptable as well. Okay, and part D, again, you could probably just reason it that the velocity at 2 is the same as the negative velocity of v0. Why is it negative? Because it's same speed, it's just the opposite direction. So your answer should be negative 20 meters per second. Or again, you could just solve this. You could say v2 equals v0 minus gt. So you've got 20 minus 9.8 times 4.08 seconds. And this gives you should give you negative 20 meters per second. Okay, it's really up to you how you solve this. It's also good to point out that the reason why it's negative is because the velocity is in the negative direction. All right, now moving on to part E, sorry. We're looking for the velocity and position of the stone at 5 seconds. So this is about 2 seconds up to here and then about 4 seconds there. So somewhere down here, maybe, I don't know, let's just put this point 3 here. So at this particular point, we know that the time at 3, we'll just write t sub 3, you can call it t sub 5, it's up to you, is 5 seconds. And so we're looking for the velocity and the position. So v at 3 and the position y sub 3. All right, so for part E, there are two solutions in here. The velocity, you can use v3 equals v0 minus g times t3. And so that would be 20 meters per second minus 9.8 meters per second squared times 5 seconds. And this gives you an answer of negative 29 meters per second. And then for the position, you could use a similar equation over here. You could use y sub 3 equals y initial plus v0 t3 minus 1 half gt squared. There's a little 1 in here, I see that there. Okay, and then your initial position is 50 plus 20 times 5 minus 1 half times 9.8 times 5 squared. And that gives you an answer of 27.5 meters above ground. Again, it's important to tell me with reference to what. By the way, you would have got an answer of negative 22.5 meters here had you decided to put the origin up here. And the reason why you would have a negative 22.5 meters would be 22.5 meters below the top of the building. Okay, now we're looking at the position where the stone, the velocity of the stone just before it hits the ground. Now there's position 4, and remember that the stone hasn't hit the ground yet. It's just before it, right? So it's still in the air, so we're looking for this velocity v sub 4 here. It is going to be a negative number that is bigger than what we got after 5 seconds. Okay, so what kind of information do we need to know because we don't know the time that it takes to get to 4. I suppose we could go ahead and try to solve g. That's a possibility. But you do know something. When it comes, it's right at this position, location. Hopefully you got it. Y4, the position, the vertical position when it hits the ground is 0, or approximately 0. It's like 0.00001 or something like that, just above the ground slightly. So we could just say it's 0 meters. Okay, we're going to use that to solve for the velocity, right? There's a number of ways of solving it. I am going to just use v squared. The speed at position 4 is equal to v initial squared at the initial point 0 minus 2 times the acceleration times the change in vertical displacement, right? Or if you want, you could write that as y4 minus y sub 0. All right, so v sub 4 squared equals the initial speed, which is 20 meters per second squared, minus 2 times the acceleration. This should be a g, by the way. Negative 9.8 is here and here, meters per second. And then the final position is 0, and the initial position was 50 meters above the ground. That's going to give you 1380 in meters squared per second squared. And then now we're solving for the velocity at 4. Remember, when you take the square root here, you're going to have to do plus or minus 1380. And you need to choose the logical solution, which is going to be a negative answer. You're going to reject the positive because remember, it's going downwards when it hits the ground. And this answer is negative 37.1 meters per second. The reason why we have a negative is because it's going down. Okay, last part. What's the last part asking for? The total time the stone is in the air. Now there's a number of ways to solve this again. I already know the final velocity, right? So I could use that. I could use v sub 4 equals the initial velocity 0 minus g times t sub 4 and solve for t. So this is negative 37.1 meters per second. Remember, if you don't put the negative in here, by the way, you're not going to get the right answer. So it's very important that you have the right sign. And the initial speed is 20 meters per second minus 9.8 meters per second squared times t sub 4. You're going to get negative 57.1 meters per second equals negative 9.8 meters per second squared times t4. And this gives you an answer of 5.83 seconds. There are a lot of ways of solving this question, by the way. Some people I see often use this equation, y sub 4 equals y0 plus v0 y t sub 4 minus 1/2 gt squared. The problem with this one is that you'll have a quadratic. You'll have a number here, a number here, and a number here, and you have to solve the quadratic equation or graph it. And that's fine if you solve it using the quadratic equation. You don't have to show the solving of the quadratic equation. You could just say, I used my calculator and I graphed the zeros and I got this. Another thing that's interesting is that you could just graph this whole problem. I think that's a great idea to do that. And if you have your calculator, why don't you try to plot the following equation? We had y as a function of time equals v0t. Actually, the initial position plus v0t, and then minus 1/2 gt squared. And let's substitute in here. Y as a function of time equals 50 was the initial height, plus the initial speed was 20. We'll just leave t in there as a variable, minus 1/2 times 9.8 t squared. So y as a function of time equals 50 plus 20t minus 4.9 t squared. And now what I'd like you to do is plot this on your calculator. We'll have y here on the y-axis and t on the x-axis. And you should get something that looks something like, I don't know, like this, like a parabola, right? And this height initially was 50, right? This point right here at the apex of your curve will be the time of 2.04 seconds. That was what we got in part A. And the coordinates of that will be 70.4 meters. And you could find the maximum on your calculator, I'm sure. You could go all the way over to here where it's back to 50, and this would be, I think, 4.08 seconds. You could also go to, say, about 5 seconds here, and you'll get to here, and then this is referring to a height of 27.5 meters, which is the answer we got in part C. And then you could see where this actually finally intersects the axis, and this will be a time of 5.83 seconds. So you could get all of the vertical information and all of the time that we were solving in the earlier part. Furthermore, we could get the velocity by using v as a function of time equals v0 minus gt, or 20 minus 9.8t. So once you know the appropriate time, you could just plug it. You could plot that graph. It would look like something like this, you know. Anyway, we'll talk about that in class. But it's good to also see, to look at this through a graphical means, and you'll learn a lot more about the physics that you're doing. Okay, that's it for this already rather long problem.